Okay, great. Yeah, hello everyone. I'm Phillip Moesta. I'm giving this talk remotely from Amsterdam. And I decided to talk about GRaMX, which is a new GPU accelerated dynamical spacetime GRMHD code that we developed in the group here. This work has mainly been led by a PhD student here in the group, Swapnil Shankar, who I think is also in the meeting, and then has been done in collaboration with the Carpet X developers. And yeah, I'm going to give a little bit of an update of where we are in development of the code and what the next steps are, and slot that into what we want to do with the code ultimately. So, I mean, we've already heard some really nice introduction by Sebastiano, and also Samuel this morning on neutron star mergers and what's important in evolving them and how to construct initial data for them. But more generally, I think the applications that we have in mind for this code is really anything where you can put magnetic fields and high energy astrophysical phenomena. So the current application we're mainly developing for is the supernova regime, where neutrinos are important, where turbulence is very important, magnetic fields in particular, subgroups of supernova. But then ultimately we want to apply the code as well in binary neutron star mergers, potentially binary black holes plus accretion disks. But this is going to be a step-by-step development process. And I don't have to motivate this much here, but since we may also have students in the meeting that are relatively new to the field, this is really an exciting era of what we call transient science, since we have all these wide field time domain astronomy missions like ZTF, DCAM. Remove the tab coming in between. So you want the... Is this better?
Yeah.
Perfect. So all of these missions really scan the night sky multiple times per night and provide a wealth of observational data that, in combination with detected gravitational waves from advanced LIGO, really puts us in this new era of like doing multi-messenger astronomy with these events. And at the same time, we really in the last 5 to 10 years have computational tools that are really at the level where we can model these events from first principles on some of the biggest supercomputers that are being built right now. So this is really a transformative time that is ahead of us. We're already in that transformation. I think Sebastiano also highlighted some of the challenges that come with, making our simulations more high fidelity, more faithful, so that we can actually interpret all that observational data with the right tools that we have. So what are some of these events that we're interested in? We already heard about neutron star mergers, but beyond that, in the supernova realm, there's a lot of transients going off in terms of both normal supernova, which you see here, an evolutionary diagram in the top of this talk, where we have a massive star undergoing core collapse at the end of its lifetime. It collapses all the way to forming a protoneutron star, at which point a mechanism or engine for the supernova is forming. And then here I'm just highlighting very broadly 2 different categories of these explosions. So the normal supernova, these are in principle 99% of all the supernova that we observe. The core collapse supernova typically have 10 to the 51 ergs explosion energy. There's also some events that are more extreme. So this could be explosions that are more luminous, so where the light curves are much, much brighter. There are explosions where the kinetic energy of the ejector is at least an order of magnitude larger than in regular supernova. So these are called hyperenergetic supernova. And some of these special supernova also come with an additional long gamma ray burst detected in coincidence. And so there's a lot of questions about like, what are the engines driving these more extreme events? For the regular supernova, I think we mostly as a community have agreed on neutrinos being the main agents of driving these explosions. The details of these explosions and which stars exactly explode and in which way and what elements are made are still being investigated. And and as open areas of research. But overall, I think we understand how most of the core collapse supernova explode. But for these extreme supernova, it's a little bit more tricky. And there are lots of observational evidence for this. So like we have a sample of like these core collapse supernova that are associated with GRBs, for example. They all seem to share some characteristics. So none of them have retained their envelopes, meaning that they don't show hydrogen or helium in their spectra. They also show outflows that are moving at least mildly relativistic, as inferred from the Doppler broadening of the lines that we observed from the spectra from these events. So there seem to be more extreme conditions at work here than in regular supernova, where, for example, the typical speeds of a shock in a regular supernova are more like 10,000 kilometers per second. So significantly non-relativistic. But then it's also not that all of the stripped envelope supernova we observe automatically come with GRBs. So there seems to be some additional parameters, either of the progenitor or the engine that is forming, that determines if we get an additional GRB, or maybe the GRB doesn't fully make it out of the star. So there's a lot of open questions of like what actually happens in these extreme explosions and what the observational outcome is. All of these events seem to trace low metallicity environments, and some of the superluminous supernova that I mentioned earlier share similar characteristics in terms of their host environment, in terms of the galaxies that they happen in. So there's a lot to figure out here. On top of that, and I think Sebastiano also made a beautiful case of that, in neutron star mergers, we have again demonstrated the massive potential that lies in multi-messenger astrophysics, but there's open questions here too. Especially, I'm just focusing on the ones that impact more on the magnetic fields and the remnant phase of the merger. So what kind of remnant do we leave behind? How long does a potential hypermassive neutron star or hypermassive remnant survive until it collapses? How does the short GRB operate? What's the engine behind that? Is that a black hole, a magnetar? How does the jet make it out? Is it a structured jet, top hat? And then how do the different ejector components combine together to ultimately make the kilonova observations and the different parts of the kilonova? So I think there's still a lot of open things, a lot of open questions that are unaddressed in the sense of even what we can do with current advanced LIGO and EM observations of these events. So really this kind of brings us to these classes of events that we see and where we don't fully understand what the engine or the potential multiple engines that could lead to these different observational outcomes can be. And the question is like, what are these engines and how do we figure these out? And I'm going to kind of sketch out how we do this with simulations typically, and how GPU accelerated codes can help us do that better or in more detail or for longer times. But ultimately, really, as a community, what I think we have to establish, and I think that there's multiple avenues towards that, is like to connect progenitor system parameters to the observation super simulation of particular star explode. You can use suites of these simulation data to actually then impact physics knowledge about does that look like if we put it to work on this something, but just continue, please, as in to the.
So we are back.
I think I'm just the same problem.
Okay.
Do we have a wired connection maybe here? When the room is ready to go, you can put something in the chat to have to keep track of that.
Yeah.
Okay, can you try speaking? Nothing.
He is speaking, is what he says.
Okay, so let's wait. I'm gonna try to put this on. Mute that. Okay, can you hear us?
Yes, there's a lot of echo though.
Oh, we lost them again.
Audio session.
Okay. Go back to audio. So I think it's working out. So
I think I might just make it my own.
Okay.
okay, connect back audio. Hopefully that'll work.
Should we try?
Okay. Are you speaking?
I think he might be speaking.
Okay.
Almost dead. Like the batteries of the computer said it was almost dead.
Yeah, that's why it's,
plugged in.
yeah, it's plugged in and charging. It's just, we can't connect to his laptop either with the like connections that we have.
Okay.
Okay. So
So that's the issue with my MacBook dying.
Okay. Didn't we have a connector that worked for the mini DVI? Then we've got my laptop, but that's gone again.
We did have something like this.
Okay.
Can you hear us now?
I think we online seems to be fine, but the room is lost.
Yeah, Roland just said try again, please. Okay, they can hear us. Can you also see the slides, or how does it work?
Yes.
Okay, so if you mute yourself, can you speak and you can hear us well?
Yeah, my volume is close.
okay. Can you continue?
Okay, yeah, I can continue. Okay, so where did we leave off? We left off with some simulation of a supernova that I'll just replay while I'll get back up to speed. So this is a demonstration of what we had done on CPUs before I think this particular simulation took 2 to 3 months on like 10,000 cores back then, but that's also almost 10 years ago. So of course, nowadays one could do these simulations more easily and more cost effectively. But still, if you look at the time in the simulation that's shown at the top, it's really only covering the first 200 milliseconds after collapse of the iron core to a protoneutron star. If we really want to track this explosion further out into the star, for example, not even thinking about the total length scales that are involved for the star, but even just saying until we can figure out how much nickel, for example, which is the main radioactive element that powers the light curve from these events, even if we want to figure this out, we would need to at least go to like 10 to 50,000 kilometers in terms of where the explosion needs to be tracked to. So this requires much longer timescales and much longer simulations to access those features. So then the question is, how can we go there? And just to summarize what we need to include in terms of the multi-physics challenge that these simulations pose, and similarly, neutron star merger simulations really pose the same kind of challenges. We need magnetohydrodynamics to handle the gas and the plasma dynamics. We need general relativity, and in this particular case, and even more so in the neutron star mergers, we need full dynamical spacetime, general relativity, full numerical relativity simulations to handle the collapse of the iron core to a protoneutron star, the relativistic jet that's propagating, and in the neutron star merger case, of course, the merger and the last final few bits of the orbit. On top of that, we need nuclear equations of state. We need the nuclear reactions between the different isotopes, and we also need the interactions of that material with the neutrinos that escape in the system. And then ultimately, we need a full transport theory for the neutrinos, and that really adds 6 extra dimensions to the problem by basically evolving the full Boltzmann transport equations if one wanted to do that correctly. So this is really all 4 forces fully coupled. It doesn't stop there. We have to include things like rotation and deal with fluid and magnetohydrodynamic instabilities. We need to deal with multidimensional structure of the progenitor systems, of the turbulence that's evolving, and at the same time access vastly different spatial and temporal scales. Just to give you an idea, the turbulence around the protoneutron star, we need to resolve down to a level of at least 10 or 1 meter. At the same time, the scale of the star, the system scale, is at least a few million kilometers. So really this gives you a massive problem in scale. The same applies in terms of the time step and the total time of the system that we need to evolve. So really we need cutting edge numerical algorithms, sophisticated open software infrastructure, open source software infrastructure, but also software infrastructure that we can put to work on current peta and exascale supercomputers that are around. So that's really the challenge. And this is, I think, where we positioned this new code, GRaMX, to make use of what modern hardware infrastructure looks like. And the reality is that modern high-performance computing systems have the majority of their compute power now in GPUs. Many of the systems have the CPUs mainly as like hosts for the compute nodes, but the majority of compute power is in GPUs. Of course, there's still CPU machines around as well, but if we really look at the recent ranked supercomputers, the top few ones are mainly dominated by GPU performance. So this really creates a need for having GPU-ready codes to be able to use that computing power, but even more so to even be able to access these machines. And if your code can't utilize GPUs or potentially other accelerators that come along in the future, you won't be able to even write a proposal to get an allocation on some of these machines. So the code we developed, and this was really work led by Swapnil, has been deemed GRaMX, General Relativistic Accelerated Magnetohydrodynamics on AMRX. I'm going to go into the different components that come into this in the next few slides, but GRaMX is basically a complete redesign of what was or still is GR Hydro within the Einstein Toolkit framework. And we were initially thinking about like how to best make this transition, but then ultimately decided that a complete redesign is the most favorable route to go. The goal is really to have a code that can perform simulations of core collapse supernova and neutron star mergers on GPUs on the exascale, so on the world's fastest supercomputers. GRaMX has really been developed on top of CarpetX. I think Eric gave a beautiful introduction to CarpetX yesterday. So it utilizes many of the features that CarpetX provides, relies on it for mesh refinement, input-output, inter-node communication. And of course, CarpetX in turn uses AMRX for doing the actual mesh refinement implementation and launching compute kernels. And in particular, the launching compute kernels is something that we heavily make use of for actually writing our application level code. So how does this all fit together? And this is really where basically first we have AMRX, which is an adaptive mesh refinement library developed for use by the Department of Energy's exascale computing project. So this is mainly driven out of Berkeley National Lab and ties into many of the application codes that build onto AMRX. One of the key benefits in this is that there's continued funding for AMRX by ECP and also support of the community, a relatively large user base with different levels of application codes that hopefully provides for a stable basis also for CarpetX in the future. And then in the bottom of the slide, really, basically, this is how this works together for the code we're building. So you have application thorns like GRaMX, for example, but could also be AsterX or some other application thorn that sits on top, interfaces with AMRX through CarpetX. So the application thorns themselves don't need to necessarily know exactly how to operate within AMRX. And then all of that is tied together by the Cactus Flash as per usual, and as was the case for Carpet. And so then some of the transitions we made, and I think many of these are not exclusively done just by the group here in Amsterdam, but like on the left, you see the CPU equivalents for Carpet and for example, GRHydro, ML, BSSN, but then also some of the more infrastructure related thorns like ADM base and Hydro base where variables are stored and defined. And how we deal with that based on CarpetX, where you could have your MHD code, in this case GRaMX, but this could be another application code as well. Really for spacetime evolution, we're mainly using Z4C, and then some of the other thorns really stayed the same, but have been re-implemented for CarpetX. So what's different between GRHydro that was based on Carpet, or still is based on Carpet, and GRaMX based on CarpetX? One key difference is that we now have lots of different variable centerings available. So that allows us to do some fancier things for fluxes. We could potentially define magnetic fields on the faces and things like that. In GRHydro, lots of loops over grid points were done using for loops or macros. This is now done via specialized lambda functions in GRaMX. I'm just going to show an example about over this in just a second, which really deals with the loop. And this is mainly to utilize the offloading functions for kernel launch later on. And then GRaMX can run both on CPUs and GPUs, while GRHydro mainly can only run on CPUs. So, additionally, GRaMX we've written completely in C++17, mainly for some of the features that we needed. Where GRHydro is a complete mix of C, C++, and Fortran. Of course, that could be cleaned up to provide a similarly level of clean implementation. Just to kind of provide a little bit more detail about how we deal with staggered grids in CarpetX and GRaMX. So we typically have the spacetime variables vertex-centered. We have face-centered, for example, in this particular example, in Y fluxes, and then fully cell-centered variables for the hydrodynamics. Again, one could extend this to deal with magnetic fields at different centering, potential electric fields to update your terms. So there's a lot more flexibility in how this is being defined in CarpetX and via that also in GRaMX. To give you an example of how actual application code looks different and GRaMX versus GRHydro, you see the example of just like a very simple setting a grid function variable to 10 at all grid points. You see that at the top done in CarpetX, GRaMX, and the bottom an old example from GRHydro and Carpet. In principle, for the user application code, if you don't necessarily need to deal with the actual offloading, the actual lines of like doing this doesn't really differ. There's some detailed differences in how you access the actual grid function index, but besides that, you're just setting a variable to 10. So that's not a big deal. But then of course, the loop construct itself looks quite different, and some of the parameters and how that CCTK device and loop all devices done basically enables the offloading to the GPU. So this is something where you just get used to a different kind of environment to program in. But other than that, for a new developer or someone wanting to add a new development on into the new CarpetX infrastructure, that's really not going to be a massive learning curve to get used to the new way of doing this. The main parallelization strategies we use in terms of running on GPUs is really via GPU offloading. So this can be done via CUDA, this can be done via HIP. This all interfaces technically also with multi-threading via OpenMP and MPI for distributing across different GPUs and different nodes. The good thing about the GPU offloading is that this is mainly handled by MRX under the hood. So you can, of course, make choices, and some default choices are being made there, but this is something that we don't have to reinvent for our application codes, something we can't make use of the extensive expertise built up in that community. How does the actual parallelization over GPUs work? So this is just a single refinement level simulation example where you see the different boxes in different colors in this 2D slice through the domain. The boxes are just simply divided among the available number of GPUs, and then we do standard things to fill ghost zones of a given box. In an AMR example, this looks a little bit more complicated, as now basically each GPU handles one or more boxes per level, but basically you can see again in the different colors, which indicate the different GPUs, that, for example, in this particular example, each GPU has a box from each refinement level. And this helps us with doing the mapping of GPUs to MPI ranks. This is mainly handled by MRX, but then the prolongation and restriction is still handled by CarpetX. This seems to be a favorable way of parallelizing for now as we interface with AMRX. Some important parameters just to mention here, max grid size really handles the size and the number of boxes that are created. This is quite important for MPI parallelization. Tile sizes would be important if you also use OpenMP in parallel, and then the blocking, particularly the max grid size is a crucial parameter if you want to perform efficient simulations on GPUs. So current features of GRaMX can do spacetime evolution via Z4C. So this is not an inherent feature of GRaMX. It's an ideal GRMHD implementation using the Valencia formulation. It really follows the exact same methods as GRHydro did, can do 3D AMR. We have analytic and tabulated EOS support, different reconstruction methods. Currently, we're using Reno 5 for most of the stuff we're doing, HLL remount solver, and currently a leakage scheme plus an M0 scheme. We're working on porting the M1 scheme that David and Sebastiano have developed and that we've used with GRHydro on CPUs already. We're currently porting that over as well. So all of these features, tying back to the original slides on like what is important in terms of the physics playing a role in core collapse, supernova, neutron star mergers, all of these are crucial to have in the mix. To verify that the code is doing okay and that we're recovering known solutions while we perform a number of tests in 1D, 2D, and 3D. This ranges from 1D, typical MHD sharp tubes, magnetic rotor, cylindrical explosion, and then we've also done some dynamical spacetime tests, TOV oscillations, and we're currently running, so Neil is currently running the first application simulation where we run a full 3D supernova explosion with neutrinos. In the interest of time, and I think because most people are familiar with these tests and or can look them up in the paper, I'm going to skip over basically demonstrating that the code is behaving well, and just jump a little bit more to the performance section. For that, we've done some various tests on supercomputers like Summit and Crusher. So Summit is basically the now previous generation biggest DOE supercomputer utilizing GPUs, and the new supercomputer Frontier has just basically been launched into production or pre-production, and they have a test system that emulates the same hardware called Crusher. To give you an idea of like how these compare, so the typical Summit node has 6 NVIDIA V100 GPUs. Their peak performance is 8.2 teraflops per GPU. And so we've done some scaling tests to figure out how we perform on these systems, both weak and strong scaling, and see how the code performs. This is the weak scaling for a few different setups that include slightly different configurations in terms of how many cells we put to work per GPU and how many physics are included. And this is mainly due to the GPU memory basically setting an absolute limit of how many points or how many cells we can put into a box onto a single GPU. You see that there's quite a high drop in efficiency initially, going from basically when we just run on one GPU versus when we go to multiple GPUs, since that's when communication comes in. But beyond that, we actually get then really good scaling for weak scaling, going from one node to multiple nodes. We've run this all the way up to 13,000 GPUs or roughly 2,000 nodes on Summit, and get pretty good weak scaling efficiency beyond that. And one thing, of course, that one would want to do, and that seems to be beneficial for overall performance, since this is just scaling, would be to have the largest amount of points per grid that you can hand off to a single GPU. But then again, that seems to be mainly limited by memory requirements on how many registers you have available in terms of how many variables you can effectively store onto the GPU. We've also done strong scaling, but basically just saying that that's typically not a well-matched metric for the GPUs, as the smaller sizes you give to the GPUs, the more compute power onto the GPU you actually waste, since then you're not really saturating the GPU with actual work. So that we're not doing as well as in the weak scaling. And we have recently done the same on Crusher, so where we've basically, this now has AMD GPUs. They're about a factor of 4 faster per GPU than Summit. And they also have 8 of these GPUs on a single Crusher node. We've not gone, since Crusher is a pre-system, and this is a plot done by Eric, where we've only gone to 64 nodes for now. We're currently waiting to get access to Frontier to see how we do there when we go to larger core and node counts, or GPU and node counts. And then currently, I mentioned this, we're running the first production simulations with the code. So it's a full dynamical spacetime core collapse supernova simulation. So this is GRaMX for GRMHD, Z for C for spacetime, and then neutrino leakage plus an M0 heating approximation, starting from a MESA generated initial progenitor star. This is 9 levels of mesh refinement. And we're currently running at a low resolution, and the goal is to really push that simulation potentially to 1 to 2 seconds of post-bounce evolution time. To go back to what I initially showed in terms of the movie, that would be a factor of 10 longer than what we have done a few years ago, where we really only access the first 200 milliseconds. This will really be a game changer of what we can do. Currently, that simulation is early on. We've just gone through the early post-bounce evolution. You see a plot of the central density here. Where we're really only looking at the first initial 20 milliseconds. But this is really the first production level simulation that we're running. In terms of performance, to give you an idea for this supernova simulation, which is really kind of a production level setup, again, 9 levels, 72 cubed cells. This takes about 6 node hours to do a few milliseconds of post-bounce evolution. But if we think about a larger setup that will allow us to go to longer timescales, also meaning larger domain extent, we estimate that we need about 1,000 node hours for like 100 milliseconds post-bounce evolution. So that would really mean that with a typical allocation of like 1 million node hours, we could do 1,000 of such simulations, which It's like just a massive change in order of scale of what we can access. Even if we want to do like second-long simulations, we could easily do hundreds of those for 3D simulations, which, just to contrast that to what the current kind of state of the art with CPUs is, where you do, maybe order 10, not even order 10, you'd maybe do 5 to 10 of these simulations on CPUs in 3D on a given allocation. So this is really a massive change in what we can do. And this will allow us to both do faster simulations, but also much more cost-effective simulations to figure out, what different progenitors, for example, do, how different stars explode. But we can also potentially look in more detail at the turbulence plays a role, for example, in how the explosion is driven. With that, let me summarize. I've introduced GRaMX that is built on Carpet-X and shown that we get really good single-level unigrid simulation performance at up to a factor of 10 faster than on equivalent CPU systems. In AMR, it gets a little bit more tricky, but we are getting there in terms of the performance as well. But really, this allows us to do basically an order of magnitude more simulations with or like actually almost 2 orders of magnitude more simulations with the same allocation. We compare current CPU allocations on the fastest machine versus GPU machines. And this is just the beginning, right? There's a lot more optimization that is currently being done that is needed, especially, for example, for Z4C. I think many of the codes that also interface with Z4C, we share a similar need for upgrading what we can do and how we can do this more efficiently. Same applies for neutrinos. So there's a lot more potential for more speed up to come. And I think in that way, the future on GPUs with the Einstein Toolkit is hopefully bright. And let me thank you for your attention.
Yep. All right, just to double check, Philip, you can hear us?
Yeah, I can.
Then we have about 5 minutes for question until somebody needs to get their coffee right now. So any questions for Philip, or I guess for Sebastiano, if there are no questions for Philip?
I guess the obvious one for GRaMX is there potential for this to be open sometime in the future, like down the line?
Was that all?
Can you speak up a little bit? It was barely audible.
I mean, this is obviously excellent work, and you'll get a lot of physics out of this. But I mean, is there expectation for GRaMX to be open source at some point, or?
Yeah, so we do plan to make it open source sometime next year, but it's basically just mainly Swapnil working on this right now, and I just don't have the person power in the group to like currently make it open source, but that's planned for next year. So probably towards the summer next year or towards the fall, we do plan to make that open source, and then also discuss how we can include that in the Einstein Toolkit.
As a follow-up, like, do you see Eric talked yesterday about how subcycling isn't yet implemented, or at least reliably implemented. Is this another optimization that you think will have a big impact with GPUs, or not so much?
I actually don't know. Like, I think we initially kept it simple and didn't deal with subcycling yet, mainly to not have an additional level of difficulty to deal with there. I mean, of course, in principle, subcycling can save you a lot of time. I think I just don't have good intuition yet on how complicated that will be to do on GPUs. So I think that's something where it remains to be seen how much of a speed up that can be. But if we can implement it in a good way, I think, of course, this could save us a lot of time, especially if you think about these supernova setups, 9 levels of mesh refinement. Of course, there could be a lot of time gained there.
Thank you.
Thank you. Are there any more questions? No, there's too much drought for coffee, it seems. All right, so thank you both very much for the interesting presentations. Thank you for bearing with us for having technical difficulties. And if you two are around during the break, I guess there might be some more questions that people might want to ask in person via chat, or just walk up here and use the non-big speaker. Thank you very much.